Okay, let's start lesson 2, the spice simulations. And spice is very popular simulators, and this is the first simulator you may use. And spice means simulation programs for integrity through video. And spice simulation, we have mainly 4 kinds of spice simulations. We have DC and operating point analysis, AC analysis, transient analysis, and harmonic balance. And we have to understand the simulation principles and the characteristics of each meaning. So first we are starting with DC analysis. DC analysis. On DC analysis, the capacitors do not care, so we ignore capacitors. And inductors do not care, it's just short. So in DC, the capacitors are open and the inductors are short. So this kind of circuit is becoming like this. So here, because this is DC, all the voltage and current source are constant, and capacitance is open and inductor is short. And in transistors, the transistor is replaced with voltage, control, current source, and capacitance and resistance, but we can ignore capacitance. So here. First we want to understand how spice simulator simulators. So in this case, many Japanese, I'm sorry. Kirchhoff current law. And in point A, we can have a current source going into here, and the current going out from VA to this way by G1 times VA. And current goes from A to B like here G2 times VA minus VA. And at point B, and the current goes out like G2 times B minus A, and G3 times VB, and G4 times VC minus VB minus VC. And we can write down all outgoing current in I equals GV form, not V equals G. Not V equal VV format, but in SPICE we use I equals GV format. And these equations can be expressed in matrix form, like this. So here we know that this GII elements. GII elements is the sum of all the conductance connected to the node I. For example, in here VA, so VA is here, so this element is all the conductance on G1 plus G2. And here for node B, the element becomes to be G2 plus G3 plus G4 and something like this. And also we have this element and this element for concerning about the voltage source and current source. And these elements put minus on the conductance between I and J. So in this case, node between the node A and B, there is a G2, so minus G2. And also node C here, this means node C and node B. So node C and B, so this is G4, and so we put minus. So the the important thing here is circuit connectivity feeds these equations automatically. Once you know the circuit connectivity, we can automatically generate this matrix. And once we have these equations, it is not our job to solve this. It is mathematicians' job to solve how to solve these equations by parts and use low amount of memory. So we don't have to care about how it's solved, but we want to care how we make how we make this matrix. We don't care about how to make inverse matrix of this, but we have to know about how we form these equations. And in this case, usually, if we have only current source, we can see GB equals C format, meaning I equals GB format. So we call this nodal analysis. And our circuit could have voltage source here. This is voltage source, current source and voltage source. And if we have voltage source, the nodal analysis a little bit modified. So we call this analysis as modified nodal analysis. So in this case, for example, if we have only resistance, like here, we have formed this modified nodal analysis matrix and calculate the inverse of this matrix and apply that for the left side. We can automatically have these values. One time is enough. But we have nonlinear elements. We cannot get the result only one time. We have to iterate our calculations. So in this case, we have current source models. That means in this case we have V in and VDD and ground. And for example, we apply 0.8 volt here, and how is the output voltage? And in this case, we have this equation and these equations. So SPICE model have equations. The current source models like this. I mean, the drain current is depending on the gate voltage and the drain voltage source and the voltage and body voltage. And also, once we know these analytical expressions, we can calculate its differentials like this. Round ID over round G and the S and B. So once we have this equation and these equations, we use Newton-Raphson method to getting these values. So what we want to do is, once we have a gate voltage specified, we can have this curve, and we want to find the cross point as here. So in order to get this cross point voltage, we have to linearize and iterate many times until it converges. So the SPICE simulation models, first we assume there is a VK here. And once we know this VK, we know this voltage and we know this current and this current. And also we have these differentials. We can have these lines and we can have these lines. And these lines is expressed like this, and GNK means a partial difference. And if we know Vk and this current, so we can have this line equations. And this line equation then actually can be expressed like conductance and currents. So these equations are expressed like conductance and current source, and also these equations are also expressed as different conductance and current source cell. So once we have these circuits, we can have this kind of expressions, and we can have this matrix, and we can solve the V and I. That means once we decide, we assume this voltage, we can have this point, and we can have this line and this line, and we can have this crossing point. And once we have this crossing point, we have Vk plus 1. So we can have this current, and because we know this curves and this curves. So we know this point, and differential makes this line and going like this. And finally, it converges. So in summary, first we calculate current and its partial difference around the initial conditions. In this case, Vk. And after these initial conditions, we approximate the linear analysis around this bias voltage and replace this curve with a resistance and current source like this. And modified model analysis calculates the next candidate. You can, and again, linear approximation and replace and make this again, and so. And these two curves converge when the V final stays almost the same as minus minus 1. So in this case, the initial condition is here, and the second target is here, second candidate is here, and third candidate is here, and fourth candidate is going here, and finally we can have a goal as a final point. And this is how the nonlinear elements are calculated by this modified model analysis. And this method is called Newton-Raphson. And so so in here we start the initial condition from here. But if we have a good initial condition, like for example here, we can easily have going to the final point. So how to choose initial condition is a key for the DC analysis. And good initial condition lead quick and stable converge. So for example, we have inverters and we want to obtain these inverted curves. We want to sweep the input voltage and calculate its output voltage. And in this case, for example, the inverter is 0.3, and we have this point. And in order to get this curve, we want to sweep the input voltage. So first we calculate the cross point at 0.3 volt, and next we want to calculate the 0.31 volt. And in this case, we use initial condition as this result, so that we can, for 0.31 volt case, we can start initial condition from here, so that it's easy to converge to here. And for AC analysis, for example, if we have inverter has this kind of curve, and when we have this applied voltage, for example, we equal to 2.3 plus 0.1 sine to pi of t. In this case, the 0.3 is the bias voltage. So we can calculate this point. And we linearize this curve like this dotted line. And for AC analysis, we assume that we have this curve, not this curve. We have this straight line. We assume this straight line around the bias voltage. So when this bias voltage changes to this point, we use this straight line for AC analysis. So for the AC analysis, first we obtain the bias point by DC analysis, and then linearize the curve around the bias voltage. And for AC analysis, it does not trace this curve, but it traces the straight line. So for AC analysis, we also use modified nodal analysis. So for AC modified nodal analysis, we have to care about the capacitance as well. Capacitance and resistance and transductivity, which is voltage control from source. And for example, in this circuit is composite like this. And this one, these transistors are linearized. So all the circuit after all the circuit are linearized, we can easily make this kind of modified nodal analysis matrix like this, and we can easily solve these equations, and we can have this voltage and current. So we don't need iterations. We just need only one-time simulation calculations for this inverse matrix. So here the difference from DC analysis is that the linear circuit equations are complex number, because we have capacitance J omega T or J omega C, and if we have inductance, it goes J omega L. So this element has complex number, but we can solve the complex number, and we can make inverse matrix using complex numbers. And also we want to sweep the frequency. And that sweeping frequency means sweeping omega. That's all. So we can use the same equations and just changing omega values. So it is easy. So that's why we can have a quick calculation time for AC analysis compared with transient analysis. And for transient analysis, for example, which we have R and C, and we input the step input like this, and we have this kind of delay output. And in order to have these curves, we can solve a differential equation like this. For example, the voltage R and voltage C equals Ri times 1 over C integral IB. And we can solve this differential equation like this, and finally we can have this curve. However, it is almost impossible to solve analytically this equation for complex circuits. So instead of analytically solve the different equations, we solve this numerically. So in order to solve numerically by these differential equations, there are three kinds of analysis, and one is forward order, and the second is backward order, and the third is backward order. And the forward order is very simple, so I'm starting my explanation starting from forward order. In forward Euler analysis, we can have a time step h. And in h, we assume that in this period, we have a constant current decided by t equals 0. For example, in t equals 0, the input is 0, so the V out is 0. So the current going from here to here is VA over R. So the V1 after H, the V1 means the output of VR of this time is 1 over C times I0 times H times H. And once we have I1, once we have V1, the I1 is calculated as this, and by using this one, we can calculate V2. And going through this and this and this and this. Repeat this procedures. So here, the point is that during the NH, during from the NH to N plus 1H, IN is decided by Vn flows into the circuit. On the other hand, the backward Euler means during this period, n plus 1 flows. In this case, during this flow, in forward Euler, during this period, In flows. But in this case, we assume In plus 1 flows. And like this. And in trapezoidal, during here, the average current of IN and IN plus 1 flows. So we have this kind of trapezoidal, and we can see that this trapezoidal has more correct results. And once you see these equations, and these equations can be expressed like this. So in trapezoidal analysis, the capacitance can be converted into current source plus resistance. This is the important point. In trapezoidal, again, I'm repeating because this is important. In trapezoidal method, capacitance can be converted into current source plus resistance. This is the key. And once we have this circuit, we can solve this by using modified model analysis. And this is how the SPI simulator solves the resistance capacitance in transient. And if the capacitance is non-linear, meaning capacitance is voltage independent. If the capacitance is voltage dependent, this is non-linear, so we have to iterate many times until it's converged. So this is very complex, so maybe you don't have to understand the detail. But what I'm talking about here, I want you to understand is when it is like the capacitance is nonlinear, the capacitance can be converted into current source and resistance, and because this is nonlinear, we have to iterate by using Newton-Raphson. So the point here is again, the point here is that for transient analysis, the capacitance is converted into current source and resistance. And because this is current source and resistance and voltage source, we can solve this by modified model analysis. This is the first point. And the second point, if there is a nonlinear element, we can use Newton-Raphson method to convert into a final point. This is the two key points. And you don't have to know the detail about this. So in the transient analysis flow, we summarize that the transistors transistors are converted into voltage controlled current source and capacitance. And the capacitance are converted into the current source and resistance. And this current source are also converted into current, so equivalent current source and resistance like this. So and transistors are also converted into current source and resistance. So all the linear elements are converted into current source and resistance, so that we can easily solve it by multivariate analysis. And if we include the nonlinear analysis, nonlinear element, we can iterate by using Newton-Raphson to get the final result. This is what SPICE simulator simulates the transient analysis. Okay, this is a flowchart. So we set initial trial operating point first, and then linearize the semiconductor device under trial operating point. And this is the way to use Newton-Raphson. And load linear connectors in circuit matrix and solve the linear equations and judge if it is converged. And if it is not converged, define the neutral operating point and iterate like this and like this and like this. And if converged, we can have the voltage and current in that time, and then increment time. And if this is the end of time interval, if no, we define the describe the different equation and so nonlinear. So we have two iterations. If we have nonlinear elements, we have an iteration using Newton-Raphson, and also we switch the time, so we have iterate by a timing step. So this internal Newton-Raphson nonlinear iterate are inside of the loop, and this. So at every time step we have this kind of iteration, and after that we have implement and then iterate Newton-Raphson again and again. So it takes time compared with AC analysis. But AC analysis is kind of linearized around the bias points, so the result is not accurate. But in the transient analysis, it takes into consideration all the nonlinear effects, so this is correct. But it takes time for simulation. And the another one is harmonic balance. How many of you knows about harmonic balance? Harmonic balance is kind of a simulation between AC analysis and transient analysis. So for AC analysis, we specify one frequency and linearize around the bias voltage and calculate the response at one specified frequency. And in harmonic analysis, specified frequency and how many harmonics we consider. So if we consider 8 harmonics, so harmonics means it takes the nonlinear effect into consideration. If the harmonics is 1, that means only main frequency. So the 1 harmonics means the same as AC analysis. And once we have for example, 8 harmonics, we can consider more nonlinear effect, and if we have 100 harmonics, it completely traces the nonlinear effect. And we can specify, for example, 2 frequencies like F0 and F1 and their harmonics. n times del plus n times del 1, all of them are in class. And it simulates a steady state operating in the frequency. And so, and non-linearities are taken into account. And non-linearity means higher order harmonics are taken into consideration, but the problem is transient cannot be simulated. So, for example, if we design a mixer circuit and multiply 1 GHz signals and 1999 MHz signals, and the output becomes 1 MHz. So once we have mixer with mixing the 1 GHz and 1999 MHz, we will have a 1 MHz beat. And in this case, if we simulate by transient analysis, and we want to simulate more precise analysis, for example, the time step is 1 picosecond. And time step 1 picosecond, and make these mixers, so that means 1 picosecond until 1 microsecond, we have 1 beat frequency. And usually it takes time to going into a steady state for mixing circuit. So maybe we want to have, for example, 100 beats frequencies. In that case, we have to simulate with 1 picosecond time second until 100 microseconds in time. And it takes very, very, very long time to simulate this circuit. So in this kind of case, we use harmonic balance analysis. So in this harmonic balance analysis, the F0 is 1 MHz, and F1 is 1999 MHz, and let's say simulate this in harmonic balance, and we will see that we will easily get how many, the amplitude and phase at 1 GHz, 1999 MHz, 1 MHz, and for example, 2 GHz minus 1991 and 2 GHz minus 2 times 1999. This kind of many harmonies, but this kind of frequency component, how big is the amplitude and how it affects. This is harmonic balance. So for RF simulation, for RF circuit designer, often use this harmonic balance. And the transient cannot be simulated means for startup transition cannot be simulated. It's only simulated by steady state. But steady state does not mean DC. It's in AC, the steady state operating conditions can be simulated by balance. So this is the comparison. For example, we have inverters. We have inverters. And we, the bias voltage is here and simulates the input is like changing like this. And we have to simulate in DC, AC, transient, and harmonic. And this is the comparison. In DC analysis, we can have only this curve. We cannot have this kind of dynamic voltage change. And for AC analysis, we linearize this point like this straight curve. So in this straight curve, once we have input like this, the output waveform is going like this. And if we use a transient analysis by simulates of this response, the transient analysis can trace these curves. So the transient output is coming like this. And once we have FFT of this signal into this spectrum form, in the AC analysis means higher higher amplitude because we linearize this. So AC analysis result is not as correct as transient. In transient, we have this amplitude, and this is the correct result. And as long as, once we have FFT, it has higher frequency component, 2, 3, 4, 5, 6, 8, 8. And for harmonic balance, we can directly have this amplitude and phase. So, and for RF circuit design, I often use harmonic balance, and we normal circuit designer use transient. And the second topic is this is the first. Any question? So the second topic is fast spice. How many of you are using fast spice? No. So like nanosync or XA, ultrasync. No. All of you use X-Spice or Spectra.
Spectra.
Spectra, okay. And in Cadence we have ultrasync, which is a fast spice simulator. And for large circuit design, like for example, when you design memory SRAM, 1 gigabit SRAM, maybe it's almost impossible to simulate whole circuit by Spectra. Because one gigabit SRAM has 10 gig transistors. It's impossible to simulate. But yes, fast spice can simulate. And also not a simulate, not a big like some simulators, but for example PLL, such kind of it takes a long time to simulate. The fast spice can give us more faster simulation result. And the fast simulator give us more fast simulation result by using these techniques: partitioning, event-driven, time-step control, and simplified model, and automatic user-specified accuracy setup. Partitioning and event-driven. Once we have like inverter chains here, and we change the input of here, and what we want to know is the change of N1 node. And the question is, this node change depend on this transistor state. Maybe the operation of this inverter is independent of the operation of these transistors. So we can divide the circuit into pieces. We can divide it, and we call it partitions. We divide the partitions like these, and let's see. And once we change the input of this, we ignore these inverter 3, 4, and 5. We can ignore this. As long as we consider this node N1, we can ignore here. So the second inverter is converted into one capacitance and simulates these small ones and calculates the waveforms of N1. And then only when N1 changes, it calculates the second inverters using the C script. And only when N2 changes, we simulate this small loss and calculate N3. And once N3 changes, we calculate N4. Maybe this is it. So what they are doing is calculate the input capacitance Cn of each function of Cn. So that means the calculate the input capacitance of this one, and convert this input capacitance only one capacitor like this, and simulate inverter 1 and calculate N1 change, and then simulate inverter 2 and calculate N2 and translate that. So in this case, the number of elements in the modified nodal analysis matrix is 1 over 25. That means we have 10 transistors here. So in the modified nodal analysis, the matrix size becomes 10 times 10. But in this case, the element is only 3, so we have only 3 times 3 matrix. So it is easy and fast to solve the matrix. So that includes memory usage, and as well as includes calculation speed to obtain. So this is the matrix size is drastically smaller. And in partitioning, sometimes this partitioning is too aggressive. Sometimes this capacitance value depends on the second transistors. So in this case, we have inverter 1 and 2 and simplified capacitance representing inverter 3. And calculate this circuit and calculate N1, and then inverter N2 and 3 and 4 capacitance, and calculate N2, and then inverter 3 and 4 N2. And this takes a little bit longer time, but we can have more great result. But some circuit cannot be partitioned. For example, the reason why we can partition the circuit is the operation of these transistors does not affect the operation of these transistors. But in this case, once inverter 5 operates, it draws the current, the power supply voltage changes, and it affects the operation of inverter 1. So in this case, we cannot partition the circuit. So when we use pulse spikes, we have to take care of about this kind of limitations, and we have to care if we are having correct simulations or not. So especially when we are taking care of power supply noise simulations, we cannot partition. And in this case, the fast spike simulator it takes more time compared with regular spike simulator. So in this circuit simulation, Spectre gives us more accurate and fast results. And ultrasim takes more time, and it also degrades the accuracy. So we have to consider, we have to pay much attention if we have to use ultrasim or we have to use. And also the fast bias.
Excuse me, I have a question. if in the system we have two block that one block that partition and one block the partition, we just can automatically choose
yes, yes. Usually fast spice automatically read all the connectivity and automatically judge this block can be partitioned or not. And also it automatically analyze this is analog block which should not partition or which should have more accurate result than digital part which can be partitioned more aggressively. It automatically considers, so we don't have to worry about it. And for time step control, and once we have partitions and time steps are also partitioned. So in partition 1 we have, for example, if we have this kind of waveform, and we want to have a smaller time step at this point, and we don't want smaller time step like here. So in this case, once we have partitions, partition 1 we have this kind of time step, and partition 2 can have this kind of time step. So we can have different time step for different partitions. But for spectral like this, so it does not partition, so only one part shall change these other blocks in the same time control step. So it's also, so this time step control defined partitions are also included. And for accuracy, we can use optimum accuracy for each functions. So we can specify the convergence conditions and how to calculate the next stage capacitance and what kind of transistor model we use and how to control the time step for each function. And also logic circuits can use low accuracy and analog block wants to use high accuracy. So it automatically reads the netlist and automatically assign this kind of conditions. And of course, user can override the accuracy and any controls. Like these circuit blocks have to have more accurate, and this block should have less accurate but fast connections. So this is the summary of the fast ones. And usually the normal spice simulates all the blocks at the same time. So we have a large matrix and it takes time to calculate inverse matrix and we have huge memory. But once we have partitions, we can have a small number of elements for each partition and it's easy to simulate, use less memories like this. And also we have event-driven simulate that only simulates the block only when input changes. And time step control and accuracy control. So in this normal simulation, we have big matrix, and all the blocks are densely calculated. But once we have partitioned it, we have very small matrix, and we can have different time step and accuracy control. This is our fast spice simulate fast. And maybe some of you are not so familiar with spice. So this is the simple and actually I don't use vector usually. I use X spice by synopsis because I worked for a while and I developed X spice, so that's why I like X spice and I always use X spice. And for and some of you when we start studying simulations, first maybe the first thing you do is in using text editors and maybe write down the transistor connectivity line by line by text editors. Maybe that is the first thing you have to do. And after that, you use Cadence Virtuoso Schematic Editor and GUI and design a circuit by using GUI and generate netlist, and you will have a text netlist. But once you know you are used to use a Cadence and automatically generate netlist, as a circuit designer, I want all of you to know about this kind of I want you to read the netlist on text base. And for the netlist, these inverters are expressed like this. And also, this is the circuit. So the circuit are converted into netlist by Cadence. And different from this netlist, we want to make another file called stimulus. This is option something, and temperature is 27 degree, and VD is 1.84, and what kind of input we use. And sometimes we can use the Cadence schematic editor can graphically input these information. But that is very troublesome. Once you know about this kind of format, I want you to make these files by yourself by using text editor. That is more easy, and you precisely reflect what you want to do. And in this netlist, the circuit itself and the boundary condition should be written in a different files. Because this is the circuit and this is boundary conditions. And in SPICE, all elements and nodes are unique names. And node 0 is always ground. And one line has one element or one command, and plus means the plus on the right edge is a connection from the previous line. And there are comment marks switches for down. And it's case insensitive, and the oscillator shows the kind of element it is the MOS transistors or resistance or capacitance, and the first element shows it. And starting with dot is a command line, and dot current command, parameterize command. Okay, so the transistor element starting from M. Maybe it is the same as spectrum. And the H-SPICE format means that the very traditional SPICE format. And Spectre has its own format, but Spectre also reads this kind of traditional SPICE format. And starting with M, it means MOS transistors. And MOS transistors are drain, gate, source, and body, and modern name, and L equals, and W equals, N equals, ADS, And on the schematic editors, each transistor symbol has properties, and there are many properties. And in the lesson 1, I told you about this, and you have to care about LW and ABS, BDM, GS, and other items can be known. And all of these are converted into text like this. And the line order is arbitrary, and source and drain are flexible usually. And this is the NAND gate, and this is NAND gate is expressed like this. And I want you to understand from here to here and here to here. As a circuit designer, you have to understand from here to here and here to here. You don't have to understand, for example, flip-flops. Like flip-flops is kind of large circuit. So you don't have to understand the flip-flop netlist to the circuit. But this kind of small circuit, NAND circuit, you have to understand from here to here. And also we have a sub-circuit element, sub-circuit declaration, so we can have kind of a block as one block. For example, this is the NAND sub-circuit as 4 elements, and NAND circuit has 5 circuits. And sub-circuits can be instantiated by using X. So inverter sub-circuit is instantiated using X by instance 1, and the connectivity is like this. And also we have a register, capacitor, and inductors that are C and L. And voltage source, we have many kind of voltage sources. And we have this kind of pulse waveform and sine waveform and arbitrary waveform we can specify. So maybe by using text editors, you can write down this kind of voltage source. And current source are also the same, starting from I is current source. And current source can have DC, AC, power, sine. And we have 4 main analysis, DC, AC, transient, and harmonic balance. And those are also have specific formats, so we have to understand this and we want to specify what kind of analysis we want to do. And also we can include files. And usually it is case insensitive in the certain netlist, but include file and not read is case sensitive. So we can include this parameter file and we can use NG library like this. Maybe this is the same as spectrum and this one. And I often use this kind of options. Maybe it's the same as spectrum. The option for post equal to means the output waveform file is in ASCII. And maybe use a very fine time step control, like 0.01 picosecond time step control, the post version 2001 is required if we use more fine step control. And we have this kind of many options. So, and we have .ic will specify the initial conditions, and .parameter can parameterize the value, and .date we can input our data for input, and we can research the structure. So I want you to maybe and these you can look for your spice manuals and what it means, and I want you to understand these, at least these, and you can freely specify as you want. And this is A-Spice. I don't know about the spec, but for A-Spice, we have multi-thread options. So multi-thread options, and this is about spice selection. Listen to any questions? Okay, so thank you very much, and today's lesson is over.